Hello, good morning, everybody. Thank you very much for being here for another Severo Ochoa colloquium. And thank you all. And of course, thanks to the speaker today, Sebastián Sanchez. Thank you very much for having accepted our invitation. Sebastián Sánchez is a professor at the Instituto de Astronomía of the Universidad Nacional Autónoma de México, where he works since 2013. He's currently head of the astronomy observations at the Institute of Astronomy in the UNAM. He holds a degree in physics from the University of Salamanca and a PhD in astrophysics from the University of Cantabria in 2001, after which he worked at La Palma Observatory and then at Calar Alto until 2010, where he was ICTS responsible, and where he had postdoctoral stays then at the Astrophysical Institute in Potsdam, Germany, the Centro de Estudios de Física del Cosmos de Aragón, CEFCA, and our own institute here, the Instituto de Astrofísica Andalucía, the IAA, in 2011-2012. He has supervised or co-supervised a 10th of PhD thesis and a number of MCC thesis, and directly supervises the research of a dozen postdoctoral researchers. He has a long track record of teaching activities, both at his university and also being invited to give master classes in different universities, for instance, University of Victoria in Canada, the Complutense de Madrid, the IPN in AOE, or giving also international advanced schools, giving courses at those international advanced schools like the ISC Winter School, for instance, or the UNAM School. He has participated in over a dozen research projects, both national and international, encompassing both, all these basic science, the CALIFA and EDGE. I'll just cite those being PI, instrumental development, again, CAFE, data analysis software and distribution, Pipe 3D, E3D, R3D, SDS7, E-CALIFA. He has contributed to about 600 publications, amount almost 400 of them in peer-reviewed journals, about 40 as first authors with 24,000 citations, 3,000 of them as first author with an H-index of 90. In the last 2 years, he was ranked among the top 1,000 most cited physicists in the world, being the most cited astronomer in Mexico. His work is focused on understanding the evolution of galaxies through the exploration of the specially resolved spectroscopic properties, pioneering the implementation of integral field spectroscopy techniques in this field. He conceptualized and provided the community with computational methods to reduce, visualize, and analyze the stellar population and the ionized gas. He was the first to propose the existence of local relationships between the surface mass density and the star formation rate, as well as the oxygen abundance. He was the PI of the international project CALIFA that you all may have heard about, the first large-scale integral field spectroscopy survey of galaxies in the local universe, which involved more than 80 scientists from over 20 countries, resulting in over 100 publications in peer-reviewed journals, more than 50 conference presentations, and the mentoring of about 25 PhD and MCC students. This has also led the groundwork for new largest IFS, integral field spectroscopy surveys, such as MANGA, SAMI, or AMUSIN, of which he is a promoter and founding member. The relevance of his research endeavors has been recognized worldwide, leading to regular invitation to participate in evaluation panels as the ERC, ESF, HST TAC, MINECO, CONICIT. To also organizing being invited to organizing committees, scientific organizing committees for conference, on to deliver seminars and invited and review talks, and also being invited by the annual review of astronomy astrophysics to commission a review paper, Sanchez, the only author 2020, which is in fact the subject of today's talk. Thank you very much, Sarah, for having accepted our invitation. It's a real pleasure to have you here, and the board is yours.
Well, thank you very much. For me, to talk here is like to came into to my grandmother's house, it's like my house somehow. And then I came and things changed and I'm not aware of. But I feel totally at home speaking here. So I really thank the organizers for inviting me. The talk of today, after hearing all these things, I feel a bit under pressure, is about, can be summarized in basically these two plots here. Here you will see these kind of plots on the talk all the time. Here in the left, we have a continuous map image created from this galaxy, extracted from IFU data. That is the topic of today, integral field spectroscopy. And this is a three-color map created with a G, R, and I band from the news data. So it's tracing the continuous emission that is in general associated with stellar population. And this is the same galaxy seen through the eyes of emission lines. So we have a three-color image again, but in here, oxygen 3, it's blue, H alpha is in green, and nitrogen is in red. And basically, it's like a spatial resolved diagnostic diagram. So the talk of today is how we can understand the spatial resolved properties of both the stellar populations and the emission lines in galaxies and the change of the emission lines condition in these galaxies. This talk basically, it's a compendium of two review articles. The one that has been mentioned before that was invited to by the annual review of Astrophysics in 2020, and this complementary article that is everything that I wanted to include in here, but the journal said, well, this is starting to be too large. So it's like what else I could say about, and it didn't fit in the site of this review. So the talk of today is about integral field spectroscopy. I'm not going to describe in detail what integral field spectroscopy is. Just to tell you, for the newcomers, this is a technique that allows to sample a continuous or almost continuous region in the sky and obtain a spectra simultaneously of all the points that have been sampled that we name spatials within the certain field of view. There are different techniques to create this integral field spectroscopy that are summarized here, but as I told you, I'm not going to go into the detail because this will require more time than what we have. There are integral field units almost everywhere in the big telescopes nowadays. So this is a few samples in the north. PIMAS, of course, appealing to my heart here in Colorado. The WAVE, the Wheeler-Herschel, Megana, GTC. Of course, in the south, this is the king of the crown, MUSE, with all the different spectrographs. But there were previous ones, Symphony, VMOS. There are, of course, integral field units in the space. The most new ones are NIRSPEC and MIRI that are in the James Webb telescope. So you will find IFUs everywhere, and you will find IFUs exploring galaxies almost in any big telescope. So, of course, the topic of today is not only having IFUs to explore galaxies, but explore massive number of galaxies to try to uncover the patterns in the spatial resolved properties of these objects. And to me and to this institute, I think it's worth to highlight CALIFA. That was one survey that basically was directly attached to the Institute of Astrophysics in Andalusia for a long time. It length officially for 2010, 2017, but there are people in the audience that know that it started before, and later on, if you want, we can take talk about some anecdotes. There are some pictures of meetings, and I want to highlight some of my PhD students that were involved in this survey. What is an integral field? What is an integral field spectroscopy galaxy survey? Well, it's a survey on galaxies using integral field spectroscopy. So the name says everything. Of course, it has more properties than that. You're required to cover a large fraction of the optical extension of the galaxies to provide with really characteristic or integrated properties of the galaxies and spatial resolve to any galactocentric distance. The samples should be large and representative of the volume that you are sampling, because if not, then you don't have a representative result that you can generalize to a certain population in a certain volume. It may be able, or should be able, to cover or explore the stellar populations and the ionized gas and the kinematics. So all this together gives you a bulk of information that you can then you need to digest somehow, and then you need to process to understand what are the spatial result properties of galaxies. An example of this, again, is Khalifa. I have similar plots for other surveys, but it will be a bit overdoing. So we have here the continuum emission, and this is a map of star formation. The diagram, the star formation rate versus the mass for the Khalifa galaxies, and in each point we have overplot this continuum image that I showed you before. And of course, you can see here in these bluish galaxies are tracing the star forming main sequence, and here these reddish ones are basically the retired galaxies. If you go to the emission line maps, it's the same that I showed you before, so I'm not going to repeat what the color means. These are the ones that have high ionized, strong ionized gas, and they are tracing again the star formation, so that's why it's greenish, because it's H alpha is higher than the other two emission lines. And in here, you don't see it very well, but there are some pinky points that correspond to galaxies with low intensity. There are ellipticals have less ionized gas, and the emission is pinky because it's nitrogen is higher than the other two emission lines. Another information you can get from this data is the stellar spatial result stellar population properties. In this map, we plot the luminosity weighted age, and there is an example of one galaxy. In the center, the ages are older than in the outer part. The galaxies that are star forming, and they are along this star formation main sequence, are the ones that have younger stellar populations that are associated with this star formation, and of course with the ionization that we see here. So everything is connected. And the ones that are in reddish here are the ones that have all the stellar population. Of course, it's better to say not that they have all the stellar population, because all of them have all the stellar populations. These galaxies here have lack of young stellar populations. They have they don't have young stars, and that's why they are reddish here and in these colors, and why the luminosity weighted ages are older. This is again connected with the kinematics. This is the kinematic of the gas, and in here you have the galaxies that usually are rotating, are supported by rotation, and here there are the galaxies that basically are supported by, well, random motions. That are not random motions, actually. It's a random distribution in the orbit. It would be a better way to say. So this is the kind of information, and to digest this huge amount of information, we require dedicated pipelines like Py3 or data analysis pipeline in the case of Panga, Firefly, Picasso here, that was created here in the house. Because you cannot digest this amount of spectra in the typical all-way analysis of going spectra to spectra and analyze them. So there are different IFU surveys. This is just a brief summary. I don't want to enter in detail, just to highlight that different surveys are focused in different aspects. Atlas 3, that was a pioneer. It didn't sample this kind of galaxy. It was focused in ellipticals. This is just to highlight the resolution effects comparing with the same galaxy. It was focused in the analysis of elliptical galaxies in a very narrow spectral range that is highlighted here. They publish a lot. They make a lot of impact just with this narrow emission line and just focusing in the first effective radii of galaxies and only on elliptical galaxies. And afterwards, there were Khalifa and the Manga. That is the one that have sampled the largest number of galaxies, 10,000 galaxies. So for galaxies statistics, this is the survey that highlights more. In the case of SAMI, they sample just the very center, but with a very high spectral resolution. So for kinematics, SAMI is superior to the other surveys. Khalifa make a good compromise between number of galaxies. We sample of the order of 1,000 galaxies. So it's 10 times less than Manga, but we get out of up to 2.5 to 3 effective radii in most of the galaxies. So we are the one that sample and also with a better physical resolution than Manga. So we are the ones that make the best compromise on resolving galaxies and galaxies statistics. Of course, new surveys that are now the compilation of Amusing++, that is now with Muse, provide with a much better spatial resolution. But in the case of Muse, you lack This is the weather range covered by news in a yellow. You lack of the blue part, so there are important information that is missing here. This plot is only shown here just to tell you that each different survey may provide different information, and you can end up with different conclusions because they see the galaxies in different ways. So all the surveys are very complementary, and it's important to put together all the surveys to really understand what's going on with galaxies. And this is what we did in this reviews. We make a collection of all the different surveys, and we selected 2 samples. One that maximized the number of galaxies, so all the galaxies that fulfill a certain quality criteria. There were of the order 8,000 galaxies. At the moment, MAGA has still not finished to cover all the galaxies, so that was the largest compilation of a few data up to date. And then we make some kind of a golden sample that they basically have the best spatial resolution and the best sampling in terms of the galaxy-centric distance. And with that with this data is the basis of the analysis that we perform for these reviews. Okay, it does not work. Okay, we collect all this data, and then we process all the data in an homogeneous way. This is also very important. As I told you, there is a panoplia of different pipelines, different analysis tools, and each analysis tool have a different particular details. If you try to put together the results from different pipelines and you don't take care about the details, you may end up in inconsistencies. So if you want to really narrow down these effects, the best is to apply the same tool homogeneously to all the data that you have. And that's it, what we did. I'm not going to enter in the details of Pi3D. We gave a course a couple of weeks ago about it. But basically, it analyzed the data in a way that provides with the information of the stellar population, both the kinematics and the composition of the stellar population, and the composition of the ionized, the properties of the ionized gas, spaxel to spaxel. So in each location of the data that you have with the IFU survey that you prefer. So we injected this pipeline to all the data, to this compilation, and afterwards we started to repeat what had been done in the last 10 years on the topic, on the field, trying to generalize the results that have been produced. Well, this is one example of a fitting of one particular spectrum, and it decoupled the stellar population by fitting them with a library of single stellar populations, like if they were eigenvectors, but they are not. We know that they are not eigenvectors, but we treat them in an heuristic way. And from there, we have the weightings of the decomposition. From this weighting, we can recover the star formation histories and so on. And for the initial lines, we feed them with a set of models, so we can recover the flags, the velocity, and the velocity dispersion. So what we get out when we inject that to each particular data cube, for the stellar populations, we may have the average properties. This is a luminosity weighted, but you can have mass weighted. The dust, the stellar metallicity, the age, the stellar metallicity, and the dust attenuation. And of course, you may have the mass at different ages of the stellar population. So this look back time goes in that way. So this is now, and this is the origin of the universe, or the other way around. This is age. This is the older, and this is the younger. From this decomposition, you can create the star formation history of the galaxies. For the initial lines, you may have initial line maps of the intensity or the velocity dispersion for different species. And from here, you can try to recover what are the physical conditions in the ionized gas at different locations within the same galaxy. Okay, so before doing all this analysis of all this compilation, what we knew about galaxies, we knew a lot. You know, it's but the main point is that, spectroscopically speaking, we didn't have a global picture of the spatial result of spectroscopic properties. But of course, the integrated properties, we know a lot about them. For instance, in the case of the ionized gas, we knew this is a BPT, the classical BPT diagram, color code by the equivalent width of H alpha for the same sample that I described before. So it's about 8,000 galaxies, and each point here corresponds to one single galaxy. So we are treating that like a single aperture of single fiber spectroscopic survey. We could have used Sloan, but the Sloan is only sampled in the very center. So this is more generalized than the result that you can get from Sloan. This is for all the galaxies, and then we segregate by mass. So these are the low mass galaxies. The mass is rising up here, and by morphology. So then each box in here corresponds to galaxies of different morphology and different masses. And this is a result that was new before, that basically the ionization is strongly attached to the stellar mass and the morphology. If you look at the streams, these are the more massive and early type galaxies, and this is the less massive and more late type galaxies. And as you can see, the distribution in the BPT diagram and the typical equivalent width are totally different. So low mass late type galaxies are totally associated or dominated by ionization related to star formation, to OB stars. And in the case of early type massive galaxies, the ionization, when you see it, it's a combination of many things, but most of that is most probably related with post-AGB ionization and shocks, but they are not related with star formation. So this is, and of course, the intermediate type, they have a combination of both, because in this kind of galaxies, you may have bulges and disk at the same time. So morphology and mass is totally related to the ionization that you can find in a galaxy. The stellar populations, of course, we knew before. They are, again, each point here corresponds to one single galaxy. It's totally attached to the mass and also to the morphology. So we know that there is a global bimodality in galaxies. The older, the more early types and more massive galaxies are the ones that have older stellar populations that in the color magnitude or an age mass diagram correspond to a red sequence that is highlighted here. Again, the color is equivalent with of H alpha. It's going to be the same in all the plots. And as you go to later type galaxies, this is luminosity weighted, this is mass weighted. Luminosity weighted are the ones that spread more, the range of parameters that you cover is wider. For the late type galaxies, they are more located in this blue cloud here that correspond to younger stellar populations. This bimodality is totally connected with location in the BPT diagram, just to show you the same galaxies. So, of course, the ionization cannot be in here produced by young stellar populations, because there are few of those young stellar populations on those galaxies. But they are very bright. That's why if you have a few star formation in the outer part, it will highlight a lot, because these are integrated properties. Keep that in mind. Okay, so this bimodality that was known for galaxies and for the integrated properties of galaxies, it's more evident when you explore them in this diagram that I showed you before, star formation versus mass. And these are two traces of star formation, one based on H alpha and the other based on the ionizing of the stellar population. And the galaxies that are forming stars, as I told you before, they are located in a very tight relation that is known the star formation main sequence. And as you go to the more early type, and of course the more massive ones, they are located in this, now it's a red cloud that is more evident here, that they are the galaxies that are not forming a star are well below this star formation main sequence. And just to parentheses, optical AGNs are located in between, in this location that normally is named the Green Valley. These are the white points that you may or may not see, depending on the projector. And they are. That's why the people claim that they are in the transition phase between star forming and retire or quench. Retirement in galaxies, why galaxies halt their star formation, is primarily associated with the lack of gas. If you don't have ingredient for forming stars, then you don't form a star, and the galaxy is out of the star formation main sequence. So this is very well clear when you plot this mass gas, that is basically molecular gas, versus the stellar mass. Again, the galaxies that form stars are located in a tight relation that is named the the molecular gas main sequence, and the galaxies that are not forming stars, they are well below. So the primary driver or the primary association with the lack of star formation is the lack of molecular gas, and that was in different articles sometimes and so on. So this is well known before we explore with the IFUs, but it's not all the picture, because if you go to this other plot, that is the star formation rate versus the molecular gas, what we usually find is the relation that we find for star forming galaxies is what it's usually known the Schmidt-Kennicutt law or Kennicutt-Schmidt law. So they are also located in a very tight relation that is traced by these yellow points. And you may think that the early type and intermediate type galaxies, they're also following the same relation. But if you look in detail, and this is why this is this yellow line is the same in the three plots, you will notice that as early is a galaxy, as a bit below that relation is the bulk of the population. So that this is telling us that the star formation efficiency also plays a role in the quenching. Galaxies that are quenched, or they are starting not to form a star in an efficient way, they are not only quenched because of lack of gas, they are also less efficient forming stars. And there is a huge debate now, and I didn't update the references, but you can see in the literature of what came first. If it first came the lack of efficiency and then the lack of gas, or if it first comes the lack of gas and then the lack of efficiency, we still don't know. We knew before, like that we entered in the IFU galaxy surveys, that the abundance, the oxygen abundance, that is one of the more frequent elements. It's tight correlated with the stellar mass in galaxies, and this correlation you can see only when you put all morphological types together. Because if you don't put all morphological types together, what you see is some kind of a sequence. The more early type galaxies are in this regime that is basically reaching like a plateau, that is like a limit in the enrichment, and the more late type galaxies, they are tracing this regime that is like still reaching this plateau, this limit. Okay, this relation that you can see, Tremonti, different articles, and before they were in the 80s, they were pioneering the results showing that there are all these relations. So we knew all this about galaxies. However, we lack a very important result that is not new at all. It's like more than 100 years ago that Hubble told us that galaxies are resolved entities. And so this is a kind of a Hubble diagram for using IFU data from news. This is a famous or infamous. That's not the black hole. Yeah, that's saturation of the colors. This is M87 with a jet that is well known, and this is an image exactly the same colors that I described before. This is an image of contours, and this is an of a continuum, and this is an image of the mission lines. And as you can see, there is a lot of rich ionized structures in this galaxy, apart from the AGN and apart from the optical jet that you can see here. So, and the nature of that, there is a pioneering article in '94 talking about that, and this is in the archive and has never been published properly and explored properly the nature of that. But they have, obviously, it's associated with shocks. So it's these brownish colors that in this color code have a lot of nitrogen, but also have blue, and the combination of this nitrogen with oxygen 3 produce these brownish colors, and these filamentary structures are clearly associated with shocks. They have a lot of kinematic richness. And as you go to more early type galaxies, you may find in the center of galaxies also this brownish ionization. That is again nitrogen and oxygen is high, H alpha is low. This is telling us that the ionization here most probably came from AGVs and maybe shocks. And then you have a few remnants of star formation that are these clumps in green, where H alpha is higher than the nitrogen and oxygen. And as you go to more early phases, this brownish structure that is associated with the bulge is reduced to or limited to the very center, and the richness of the star-forming regions it's more evident in the disks. So when you go to galaxies without the bulge, all this structure in this ionization in the center disappears, and everything you have is a star formation. Of course, leaking of photons for this. Did you see maybe this bluish structure here? In these galaxies, it's more evident that there are leaking of photons from these two regions. You may notice also some color gradients, that in here they are more greenish in the center and more bluish in the outer part. This is more evident here. In here it's more bluish, and here it's more greenish. And this is telling us that there is a chain of the properties of the interstellar medium from the inside to the outside. And actually, this is tracing the gradient of abundance in these galaxies. We will go later on to that, but it's evident at the first sight with these plots. So the questions that why we build all these surveys like 10 years ago, and why we have been working with all this data are, well, these scaling ratios that I have described you before are global and local, and when you go to a smaller scales, they still behave in the right way, in the way that we see in the global scales, or they depart from that these relations, and at which scale this happens. So this question is still under question, and there is some light on that, but it's not a closed thing. And what these relations and at which scales they start to break tell us about the evolution of galaxies. For doing that, we certainly require integral field spectroscopy data. Keep in mind, as I told you before, that not all the surveys are the same. I insist on that. This is the same galaxy observed with Manga, and this is observed with Khalifa. And of course, this you see here the gradient of colors. So here is greenish and here is bluish. No, this is telling us that there is a gradient in the oxygen abundance. This gradient you cannot see with Manga because you lack from the outer part. So keep that in mind, because when the people compare things, tend to forget that Manga is not using the same apertures that we're using in Khalifa, and they are not sampling the galaxies up to the same scales. Not to tell you about SAMI. This is how a galaxy is seen or not seen, by the way. It's the only galaxy we have in common. SAMI is pointing to galaxies in the south and Khalifa to the north. So it's difficult to have galaxies that match in the two surveys. But the light is not the best for that. So we need a stronger projector or to be in a darker place. So here is a brownish thing that you may see or not. That is here. This is ionization by post-AGBs that is associated with this elliptical galaxy. But all the outer structure of this galaxy, it's totally lost for SAMI. Of course, if we compare Khalifa with Muse, we have also the effects of resolution, and this pinky structure that you see here in the center that most probably is associated with an outflow in the center of this galaxy. It's just hint by Khalifa. So it's like you have blurred the image that you get from Muse. Okay, so having that in mind, we jump to our topic. One of the main conclusions we get from interference spectroscopy galaxy surveys is that there is no, we cannot tell or we cannot assign a particular ionization to a galaxy in the very naive way that has been done for ages. People say this is a star-forming galaxy. This is a galaxy that the ionization is dominated by OB stars, or this is an AGN-dominated galaxy. Well, when you see spatially resolved, and this is the same colors as I told you before, I'm not going to repeat, but this is a mapping of those points in the BPT diagram with the same colors. Then you start to see things that can make you very confusing. If you integrate the spectra of this galaxy, and for whatever reason you graph that area here, you make that in the conclusion that these galaxies have an AGN because they have a very bright supernova remnant that happens to have line ratios and intensities that are typically located in the location of an AGN. And this has happened, especially when the supernova remnants happens in the very center of the galaxy, and you grab a galaxy just at very few time after the explosion of a supernova, time in cosmological times, I mean. Okay, so you can compare with what is the spatial resolve distribution for an AGN, and you can see that the location is pretty much near to that. So BPT diagram alone cannot tell you about the ionization conditions unless you see the map of how this ionization is distributed in a galaxy. Of course, if your ionization is due to pos-AGVs or low velocity shocks, you may end up in the same location in the BPT diagram, and integrating the center, you may think that this is an AGN, and but the spatial distribution of this ionization is following the stellar population. It's not centered in the central region, following like a square a power of 2 decline from the center. That is what you typically expect from an AGN, or even sharper if it has that effect. So just looking at the BPT diagram, and especially if you co-add the information, you may end up in the wrong conclusions. In a galaxy, you may have also pos-AGVs that are ionizing the medium, and they are located in this liner-like location. You may have shocks that are also located in this liner-like location, and they may or may not be related to an AGN. And of course, you may have shocks associated with bipolar outflows. Here you may see that there is a pink triangle, that it's the kinematic is indicating that it's moving out of the plane of this galaxy, and this most probably is an outflow associated with a strong star formation in the center, and it's located in exactly the same position that is associated with the other ionizations. So this pathway can only be solved if you look to the combination of different diagnostic diagrams, and also the structure that you see in the emission line maps. All these different ionizations in a way have patterns, and like we had patterns before for integrated properties, for spatial resolved properties, now here each point corresponds to 1 kiloparsec in different galaxies, combining all together of all these 8,000 galaxies. And as you can see, the distribution looks similar to the integrated one. The color, these circles correspond to the average from the center in a small size to the outer size. It's increasing the size of the circle correspond to a larger galactocentric distance from 0.15 to 2.5 effective radian. And again, the color code is the Key width of H alpha. So the pattern that was highlighted or seen before, that more, again, this is segregated by morphology and by mass. The galaxies that are more late type and less massive, they are dominated by their ionization is dominated by star formation, and the galaxies that are more late type, more early type, and more massive, the ionization, it's like a combination of pos-AGV shocks, of low velocity shocks, and so on. And so they are clearly different. However, you may see that the distribution is richer, so it's less concentrated in certain points, and the patterns also. This spread is also related to an inside-out chain. So in general, the ionization connected with pos-AGVs and also some AGNs that are bluish in here, and they are not that evident because now each spatial weight like at 1 point. So if you make the average of an entire galaxy, an AGN may dominate all the ionization. But if you take into account all the points, as each point is contributing to the plot, the contribution of the AGN is smeared out, and it's blurred from this plot. But they are still there. There are some blue points in here that are still highlighting the presence of some AGNs. So from the inner part to the outer part, you see this trend that this was that compilation in more that is it's related to what we see integrated, but it is not exactly the same. For instance, in here, when you integrate early type galaxies, you have a few early type galaxies like this S0 that I showed you before that have some bright star formation in the outer part. When you integrate, this star formation smear out the signal of the faint post-AGB contribution, and the average will be located like in here. So just a few early type galaxies with remnants of star formation in the outer part may dominate the integrated spectra, and you may think that this is the dominating ionization in these galaxies. But when you look at the spatial resolved structure, you see that the most of the locations in these galaxies is dominated by ionization that have nothing to do with star formation. Just to explain you why there is this blue structure here. On the other way, in a similar way, by the way, sorry, at the more late type galaxies you enter in the statistics, all these areas that correspond to the bulge is some kind of blur by the presence of the star formation, but here it's you see that it has a lot of contribution. So even the smaller portions of a galaxy where you have post-AGB stars are evident, spatially resolved, and they are blurred totally by the integrated properties. We have repeated that experiment that I presented in the review with the different surveys that we have published, like the final manga survey, and this that is an article that is now published from the extended data release of CALIFA, where we have enhanced the spatial resolution. And these patterns from the inside out, they are more evident and more clearly seen when you look in CALIFA. As I told you before, CALIFA is the best compromise we have even now, if you consider the lack of blue spectral range for MUs, for making this kind of analysis. And the gradients are more evident in here. By the way, this gradient here, it's telling you that there is a change in the oxygen abundance. The oxygen abundance traced by star-forming regions is higher in the center of galaxies and is lower in the outer part. So this trend in here is also telling you that there is a gradient from inside out in the oxygen abundance. So all these we have conceptualized in this scheme that I'm not going to enter in detail because, okay, so I have speaking for 1 hour almost. Okay, when you are bored, you tell me to stop because it's people that know me so that I can speak for hours. So I'm not going to explain in detail, but you see this scheme is confusing, and the message that we want to give is that indeed to disentangle the ionization even spatially resolved in a galaxy is a confusing thing, you know. So if you see that the plot is confusing, it's because this was the real mission. So this idea that we can use just BBT diagrams to disentangle the ionization, it's like a dream. You need to get back to the spatial distribution as a more simple is a galaxy, like a galaxy without the bulge. That is what we represent here, a very weak bulge. You have star formation regions that are clumps, and they are tracing the location of H2 regions clearly, and then you have leaking of photons that basically goes in that way when you look to ionization models. But as more and more ingredients you put, like you put on top of a bulge, and you put an AGN, and you put alphas and so on, everything starts to be really confusing. That's the message. Scaling relations. That's first thing. As I said, I was telling about the bimodality. I was telling you about the scaling relation globally. Now we have to go locally. So this is the local bimodal distribution between the age and the mass. Can we reproduce that bimodality spatially resolved? Well, yes. In general, yes. So you may see a different morphologies and a different stellar mass surface densities, that the galaxies may have a different kind of population, and more early type and more massive galaxies. In the more massive regions, they tend to have older stellar populations, less massive galaxies, or the outer regions, the regions with lower super brightness of later type galaxies present younger stellar populations, and the distribution also it's less evident this because there's a lot of smearing here. It has two clear peaks, so yeah, it's bimodal. That bimodality is much more evident when you explore the surface density of the star formation rate versus the surface density of the stellar mass and for star forming galaxies, there is a tight relation. There is a low statistic here, there's low statistic here, but when you have a good statistic, there is a tight relation between these two parameters, and this relation is known as the spatial resolve or resolve star formation mean sequence. So it's a parallel of the star formation mean sequence that happens is still in place at the 1 kiloparsec scale. It's a relation between the, as I told you, the surface density of the star formation rate versus the surface density of the stellar mass. And of course, when you go to early type galaxies, only that they have only star formation in the outer parts, some of them. The rest are all located below this kind of cutting line that is equivalent width of H alpha of 3 that divide basically the star forming and the non-star forming regions in galaxies. Remember that here we are not plotting, and that's also why it's less tight because the errors are larger. We are plotting here structures 1 kiloparsec scale within galaxies. For the Kennicutt Schmidt law or the Schmidt-Kennicutt law, this was known before the coming of this kind of survey, that there is a local relation. That's not a good representation. I will show you a better one later. For the mass metallicity relation, there is also a local relation between the oxygen abundance and surface density of the stellar mass. That is basically for the galaxies where you have star forming regions, that are the ones that you can measure this parameter. You see that they follow the same kind of relation, and it has a very similar shape to the relation that we observe globally. How this global and local relation compares? Well, this was a bit puzzling because the global relations that I showed you before relate extensive parameters, so parameters that are integrated galaxy-wide, and the local relations they compare intensive parameters that are divided by the area. So how you compare the global ones with the local ones? Well, in this, I follow Rob's article, Kennicutt's article, where he had a problem of measuring the distance, so he divided by the area. In the classical article, where he talked about the Schmidt-Kennicutt law in 98, and you can do the same trick. You can take any galaxy, you take this extensive parameter, and you divide by the area, and then you have an intensive parameter that is a characteristic parameter of the entire galaxy, but is intensive. So when you do that, you can plot the local relations and the global relations in the same plot. And what happens when you do that? Well, in colors are the local distribution, so each point in this color map with a color representing the density is a point of the sample that I showed you before. So there are galaxies of different morphology, and of course these are the relations that I were describing before. The resolved star formation main sequence, the resolved molecular gas main sequence, no, the resolved Kennicutt Schmidt law, the resolved molecular gas main sequence, and the resolved mass metallicity relation. And for the star forming regions, there is this tight relation that I highlighted you before. These are the retired regions in galaxies. And when we overplot the contours, they don't correspond to resolved structures to 1 kiloparsec. They correspond to individual galaxies. So I segregate the galaxies in two streams, the ones that I know that are totally dominated by star formation, the SC galaxies, and the galaxies where you may have some star formation, but yeah, they are dominated by non-star formation, S0s. So, and you see the blue contours, they are located tracing exactly the location of the local relation. So when you take a global relation, you take a global property of a galaxy and an extensive parameter, and you divide by the area, the intensive parameters follow exactly the same location as the local relations that I described you before. So This is telling you that whatever drives this relation is a mechanism that is in place from 1 kiloparsec to a portion of a galaxy to an entire galaxy. And this is a bit puzzling if you think it carefully. Okay, so we made that. This was a hint, and since we had this hint, we tried to demonstrate it more clearly. This is the global relations, exactly the same plot I showed you before, and now I selected only the star-forming galaxies, and I compare these star-forming galaxies with the star-forming regions. So the points in here correspond. These are the same relations, and we're going to explain again. Each point in here, it's a structure of the order of 3 kiloparsec extracted for the H Khalifa survey. That is a survey on Khalifa galaxies that is sampling CO, and then we can get the molecular gas. And the contours correspond to either the entire Khalifa galaxy with a tracer for the molecular gas based on the dust. And in the case of apex, it's just an aperture of 28 arc seconds diameter. So it's more or less like a 1/3 of the entire galaxy, and measured with a single dish with apex, actually. So they are the real measurements of CO transformed to molecular gas. And as you can see, the contours and the yellow points are exactly in the same location. And we publish these are the different articles where these relations appear first. So what we conclude, and we make also the more fine statistics, making fitting, comparing Comoros mineral test, blah, 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 no? But, well, the eye is the best statistical discriminator. It's obvious that they are one on top of the other. So it's true that the global relations, they are expressed in intensive, in terms of intensive parameters, behave exactly in the same way as the local relations. So, and this happens at any scale. Well, this is still an open question, but it seems that at around 500 parsecs, the relation breaks. And there are very few articles addressing that. This is a very interesting one that I don't know why we don't repeat more frequently. I keep telling, but I never have the time to repeat it because now we have a lot of data to repeat that. But it's a very nice experiment. In this article, they make maps of a molecular, the molecular gas mass density, or CO, and then you have a map of the ionized gas, H alpha, and blue is CO, and red is H alpha. And what they start to do is to measure from the peaks of the molecular gas. These are the blue points. They are making apertures, and they start to increase the aperture, and they measure the molecular gas content and the H alpha content. The ratio between these two, it's like this Schmidt-Kennicutt is the ratio of the two parameters in the Schmidt-Kennicutt law. And they repeat exactly the same experiment, but instead of starting in the peaks of the molecular gas, they start in the peaks of H alpha. So they are the red points, and they increase the apertures. And when they reach about 1 kiloparsec, then the ratio became stable, and became stable to the value that is expected from the Schmidt-Kennicutt law. In other words, this relation is can only be seen above the order of 1 kiloparsec, above the order of the biggest molecular clouds that we may find. When you go to smaller scales, this relation does not hold, and you may see some articles from fans saying that they don't find these relations at all, and I keep telling them that that's the reason, but they know. The reason for that is why this is connected is one of my latest articles, but unfortunately, I don't have time for that. I just need to finish like in 4 minutes. So gradients. Galaxies have gradients. The more evident gradient that, of course, the light gradient and the mass gradient was known before IFU surveys, but IFU surveys could measure that in a better way, and especially for different galaxy types. So this is the stellar mass surface density versus the versus the characteristic distance normalized to the effective radius. And one of the things that we have found is that when you normalize to effective radius, actually, as Rosa keeps saying, the effective radius is really effective. So many things that can be measured at effective radius are characteristics of the entire galaxies. when you normalize to the effective radiate, you can put together galaxies of very different sizes. If not, you could not normalize and put together these plots. Colors correspond to different masses, and each panel corresponds to different morphologies, with all the morphologies here. When you normalize to effective radiate, the slope of this gradient is very similar. So this means that when you don't normalize to effective radiate, the slope is very different. So the galaxies, we know that they are more compact as they are more early type and more massive, but this is an effect of the scaling of the effective radiate that is also connected to the size of the galaxy, to the mass of the galaxy. We explore the age, the chain of the age along the effective radiate, so along the gravitational distance. And we know that the galaxies in general have all their stellar populations in the central part and in the outer part. This is a pattern that is present at any mass and at any morphology, with the sharpest or the older stellar population being assigned to the center of the more massive and more early type galaxies. There is a debate of E or S0 are the ones that have the oldest stellar population in the center. But this pattern is found in any morphology and any mass. However, when you measure the luminosity weighted metallicity, the patterns are more complicated. You have a clear gradient only for the early type galaxies with a decline, and especially for the more massive ones. But as you move from the more massive ones to the more late type ones, you have a flat distribution in metallicity, or even an inversion that it's telling us that most of these galaxies are still forming, chemically speaking, from the outside in. For the oxygen abundance gradient, we have, of course, a lack of information when you have very early type galaxies, because we don't have too many star formation regions, and especially in the inner path. So in here you're suffering for low statistics. But when you have enough statistics, like in here, you have a pattern in a way that when the stellar mass is above 9.5, the abundance gradient between 0.5 and 1 effective or 2 effective radii, it's almost similar for all the galaxies. Then you have a flatter in the central part, and most probably a flatter in the outer part. And when you go to very low mass and more late type galaxies, when you have enough statistics, this became flatter and flatter. So this is telling you that there are different chemical enrichment histories in the very center, in the intermediate disk, and in the outer disk from different kind of galaxies. More recently, we explored the alpha enhancement, and we see that the alpha enhancement also depends strongly on the morphology and the mass of the galaxies. But in all the galaxies, spatially resolved, these are spatially resolved, so there are points in different galaxies, you can recover the similar trends that we have observed in our galaxy and in nearby galaxies of a similar mass. Finally, when you make a detailed description of the mass assembling history, these are results from an article of Ruben. What you find is that the center part, this is now colors correspond to different galactocentric distance. So the inner part has formed the stars before and reached the current mass in an early time that the outer part of galaxies, and this is a better measure in this way. That is the inner part and the outer part for different masses and for different morphologies. And this is the fraction of mass that was already formed with respect to the mass that they have now. The fraction of mass that was already formed at θ1, that is basically 8 gigayears. So the more massive and more early type galaxies in the very center have already formed most of their stellar masses like 8 gigayears ago. In the outer part, they are still forming the stars, but not that much. And when you go to less massive and more late type galaxies, then they have still not formed most of them, form like a 60% or 40% of their stellar mass at that time. So they have still forming a star in the last 8 gigayears. And in all cases in general, the central part has formed the stars earlier than the outer part. So this is telling us, together with the gradients that I showed you before, that in general, galaxies grow faster from the inside than from the outer side. That was a concept that was uncovered by Enrique. There are many people in the audience. There was the local downsouthing, no? So the more massive and more early-type galaxies form faster in the center of the outer part. This left an imprint also in the metallicity. So this is the chemical enrichment history of how the metallicity is growing. This is a look-back time at the different stellar masses, and this is the star formation history corresponding to these beings in the stellar masses. And this is in the center, and this is in the outer part. And metals, the metallicity grows faster and in more early periods in cosmological time for more massive galaxies than current. The less massive are still currently forming metals, and this metallicity enrichment happens faster in the central part than and slower in the outer part. And by the way, the outer part of galaxies, they look more similar between different galaxies than the center, and the distinction of galaxies happens more in the center than in the outer part. This is also reflected in the star formation rate, the current star formation rate. If you normalize by the effective radius, by the way, the star formation rate in all galaxies looks, irrespectively of the mass, it looks very, very similar, but it's puzzling. What it does not look similar at all is the specific star formation rate. More massive galaxies formed stars before, but they are not forming stars now. And actually, there is a rise of the star formation rate from the center to the outer part, or if you interpret it the other way around, a decline to the center that was uncovered in an article by Rosa. So it's not only that the galaxies grow from the inside out, also quench from the inside out. Okay, and this quenching, it's related with the lack of gas, but also with the change in the efficiency. When you plot the efficiency, the star formation efficiency at different radii, the star formation efficiency of more massive galaxies is much lower than the star formation efficiency of less massive galaxies. Remember that hint that I told you before when we saw the integrated properties, that the Schmidt Kennicutt law have some kind of a separation by star formation by morphology and mass. In the case of the radial gradients, this chain is more evident. So whatever happens in galaxies to stop forming stars, the lack of gas is not enough, or is not telling all the picture. So now I'm going to finish with some kind of, this is a compendium, there are other results. I left many things out, the contribution of many people out, but it's impossible to make that in one single talk. But we have a lot of future. In the future, I have tried to outline it here in different points. One is going to higher spectral resolution, higher spatial resolution. The connection of when this scaling relation, when all these patterns that I have telling you start to break, and why, that in general it's related to feedback, to local feedback, but I don't have time to explain. This requires that we explore galaxies with a more detailed, a better physical spatial resolution. So this is the two examples. This is FANGS. So this is M74 or NGC 628 that by the way was the PhD thesis of one colleague of us, Fabián Rosales Ortega, no? And also the PhD of Rob Kennicutt, who's focused on that article. So it's a kind of it's coming on back, and now it's one of the big hits of FANGS. This is the resolution we are getting with the local volume mapper. This is the center of the Rosetta, and I will talk about the local volume mapper next week, so I'm not going to tell too much, but the idea is to go to a smaller scales, multi-wavelength information. We need the information from the H1, how H1 transformed to H2, The connection with kinematics is still missing. How other wavelengths like ultraviolet or far infrared can give us further information. Of course, we need to go to higher redshift, and that's not the future actually, because it's even the present what's going on. But we also need, we don't need to forget that most of the things we have done with these integral field spectroscopy surveys was based with the techniques that we had at the moment. And we need to improve the techniques, because we have learned in the meantime how to extract more and richer information. Just putting you an example of something that we get out quite recently. This was the resolution that we have in the maps of Khalifa, the same kind of color maps that I showed you before in Continue, in the last data release, official data release of Khalifa. And then using different techniques, this is the resolution we can achieve, or we have achieved actually, implementing a new resolution scheme, new reconstruction image schemes. And you can see the richness, and this is an image of the Sloan. So we almost reached the natural scene resolution. What was, if you have told me like 15 years ago, I would have said that it's impossible. But people that are more intelligent than me already told me that we were doing things in a crap way. So all these reconstruction images, I'm going to give credit. Thanks for a discussion I have with Michael Blanton, that after a talk we gave him, there was on manga. He said that we are reconstructing image in a stupid way. We need to find a better way. This cannot be the best we can do. And he told me about the sampling theorem and so on. It was back in my head, and I was very uncomfortable about that, because it was the father of this reconstruction scheme until I finish finding this thing, and I still not believing too much in my own results, by the way. Conclusions. I think interface galaxies should have improved our understanding of physical processes that shape galaxies. Ionization is a local process, has to be explored in a local way. Integrated average properties of galaxies can basically destroy the information of what is going on in terms of the ionized gas. And the same happens with stellar populations. And we need to understand ionization. You need to understand not only the initial lines, you need to go to the underlying stellar population, and you need to go to the kinematics, and you need to go to the shape to basically uncover the real nature of the ionization. The evolution of galaxies seems to be ruled by local relations that generate the radial gradients. All radial gradients are the outcome of the connection between these parameters. I even said that explicitly. And they seem to be totally connected with the global integrated relations that we see in galaxies, and we have seen in galaxies for decades. So what rule these local relations is still not clear. We have learned that galaxies grow inside out, and we also have learned that the galaxies quench inside out. And I think we still don't know why galaxy quenches. And I'm totally against the mainstream of invoking like a monster that blow all the gas or heat it, and that's all. When you go to hydrodynamical simulations and you compare with real data in detail, I'm proud to be a colleague of Yago Asquesiver, that is always digging into that, and his students and now colleagues. The way that the galaxies died in either hydrodynamical simulations, we know it's wrong, so it should change. So I think that we still don't know why galaxy quenches, and that's a very important thing at different scales. So we don't know why these relations that I told you before emerged. We don't know why galaxy quenches, and all these two things are connected with feedback. So why I say that? Next week I'm going to talk about feedback. So I connect this talk with the other one, and well, I overpassed the hour. You are not asleep. So good coffee. That's all.
Okay, we can spend some time in question or comment. Please go ahead. So as you're talking about things that you're going to
analyzed when you consider just one kinematical components in your emission lines, right? So what about considering when you have several components and you're mixing everything?
Well, yes, it's a good question. I mean, there is a problem here. The problem when you start to have different kinematic components is that the interpretation of that kinematic components became more and more complex. So you either extract non-parametric, you make non-parametric fittings or non-parametric derivations like the asymmetry index or things like that that are very efficient. And then this was very efficient, for example, the PhD of Carlos Lopez. We did that for the emission sample to uncover outflows and distinguish them from AGNs and other kind of ionization. That was a very interesting thing. But when you start to fit with multiple components, normally you end up in the degeneracies, and the understanding of these degeneracies start to become really very complex. So I point you to a presentation that I think is public of Bert Husman, a former student and marvelous colleague, that made a presentation just exactly on that on the EAS in Lyon, 2019. And he started to play with the components and say, as better you fit the spectra, as less ability you have to understand what are you fitting. So just to answer you, my approach is first to make the things simple and then start to complicate, but stop at a certain moment. If you want to recover exactly the spectra that goes, the model that goes to all the emission lines, you must probably end up in something that you cannot interpret in an easy way or cannot interpret at all. So 1, 2, 3 components, okay. If you put 20 components, the fitting will be perfect. It will be perfect also with the Taylor, an SP line, but the information will become complex.
Of course, but for those in which you have detected that the presence of, let's say, 2, 3 components is important, does it have an effect of not considering that when you go into the relations you have derived blocking?
All the relations I did in here, we use a non-parametric extraction that is based on like a moment analysis, a weighted moment analysis. So they are not going to be affected that much. But if you want to go to the detail, for example, in the case of shocks or particular galaxies, yes, of course, you need to make they have an effect. And decoupling that will will not change the global patterns that are totally dominated by the mortars, the star formation, star formation. The stellar component in general, and the stellar component plus the AGN, this will dominate almost all the patterns. And then all these details that I say you, supernova remnants and shocks and all these kind of things, then you need several components, and the interpretation is more detailed than what I try to outline here. Yes, you are right. It's mandatory to do it.
Sebastián, you blow my mind all this hard work and very impressive work for the last.
I'm scared. Okay. I could be scared.
Amazing. You confusingly have shared a lot of light on the property we thought we knew of galaxies from the local scale to the large scale. So if I understand what you said in the last few slides, because I was going to ask you, you think it really is the challenge, but I think what you just mentioned, 2 main points to understand is quenching at the large scale, and then at how this relationship emerges and the slow the local scale. Now, with the local volume mapper data, you're going to address, I guess, how this relationship emerges at the lower scale.
I hope.
At the local scale. And then I'd like to connect with what Isabel just mentioned. You're going to have now, when you analyze this data, there's already the data for the local 30 levels, for example, which is very complex. You're going to have to really get into the nitty-gritty, the details of all these complexity of kinematics ionization. I don't know if you comment.
Well, I think that those who embarked in the local volume mapper, we were too naive. Became most of the people that is in there, the people that are more expert and they know better, they keep saying that there was a complex thing, but we came from galaxies, and those who work in galaxies, stars came by millions. We are like sociologists of stars, and everything is blue under the averaging thing, and now we are entering in a dilemma, because now that I see to the data, the complexity is really enormous. So giving you a short answer, and by the approach that I outlined it before, there will be some kind of a first pass through the data where we just integrate it in the brute way, like a narrow bands, moment is something like that. And then there will be a lot of refining and refining. But even when we extract all this information, the interpretation of that information is going to be really bad. So the people that make photoionization models and they create these 3D models, they will need to basically create mocks of what we are seeing to understand that. So there will be different levels of understanding of the data. I don't know if this is answering you, but it's really, well, it's going to take for ages, longer than what we anticipated, I think, by the manpower we have. But I think the data are so good, even passing this brute analysis that we are doing there, that I think we are going to encourage more people to really go into the data and try to replicate what they are seeing. But yeah, I'm not very much worried because time is all we have. So I mean, I don't have a deadline. We have the deadline for building the instrument and for putting in place, and we see Sloan consortium breathing in our neck, But now the data are there; they will be there for a long time. I don't know if this answers your question. I'm partially scared. I'm partially okay. Don't care. It's a question of time. Hola.
Several questions.
Yeah. Good to see you again. Some of the problems that you are posing here about the multi-components in galaxies are very similar to what we find in nebulas when we observe those with IFS. Great instruments, lots of data to reach complexity. We found that using 3D visualization tools or the multi-dimensional visualization tools helps a lot in disentangling different components. So I wonder whether these tools exist, whether this kind of analysis are whether we're using this.
We have different tools, but we are still for galaxies. We never. I tried to push that. I mean, the people that is in the audience, they have seen in my early presentation, these kind of cubes. And try to see, and you see, for example, jets are clearly seen and things like that, but it didn't crystallize really into the audience, So at the end, the people want, to collapse the things into the, I know, it's a question of brain.
You don't want people working on that.
No, we don't have, well.
We do have here at the IAA, people
Great.
working on visualization of 3D data.
Perfect. They are welcome. I mean, I think, yeah, to go in that line would be great. To get back to that line would be great. So, yeah, I have now I have more fundamental problems, like how to subtract the sky in the local volume marker. I'm still not at that level of detail that you are telling me, but you're welcome. If you have an idea, if you have people that are working on that, I think we will be more than happy, and I will be more than happy to talk with them and see what we can get out of that. But I'm still very far behind that in this moment.
Okay, there is another question in the chat.
Yes, Almudena, you can.
Almudena, please.
Thank you. Thank you very much. You hear me?
Yeah.
Yeah. Impressive work. I just want to mention that these large-scale laws or relations are very impressive, always impress me, but I study a parsec scales star formation in galaxies. And I can say that these laws do not happen, do not apply. You mentioned a little bit before, but I think it's really puzzling for me because I understand the large scale relations, but when you go to the real size where star formation happen, a few parsecs, stellar clusters is what we do. And by the way, this is not the future. We are doing since a number of years in the parsec project, now more recently with fans. Even they do 100 parsecs is too much because clusters happen a few tens of parsecs or less. Then things become very different. And just briefly want to mention, because this will help all to understand all together maybe, H alpha might not become a best tracer of star formation because we see many star forming regions at cluster scale where the H alpha has been leaked, it's gone. So you will miss them. Because we see star formation at cluster scale, we see them, we know the mass where the star formation has happened. So the star formation efficiency can change dramatically when you measure a kiloparsec scale, simply because the mass you integrate is much more than what is really used for star formation. There is many space in between. Or you have a huge very filling factor. The usual filling factor we use in astronomy is very tiny. Equally for star formation surface brightness, because you rate over an area which is much bigger than the region it is. Equally for ages, because when you study a star formation, you study cluster by cluster, region by in your cloud. There are different ages, and not separating by a few million years, maybe by million years. We can date every cluster in the region. And even for molecular cloud as well, because many times, most of the times, actually, the molecular cloud, the star forming region we are seeing is gone, is used somewhere else. You see more gas, more molecular, but somewhere else. Maybe it's the precursors. We see those as well, clouds, but the new coming star forming regions. So it's a little bit puzzling, it's complex. I always try to see how to connect with a larger scale. Is really difficult, but I try, definitely. But I can add one thing, is that something we are learning when we are studying this at these scales is that there is inflow gas. There is always gas, regardless of even the morphology of the galaxy we study. From the outer part of the galaxies to the regions where we see the star formation. And this must be the feeding of the reservoir of material, which is eventually, depending on what mechanism trigger star formation. I agree with you that it's not only to have the gas, there is something else as well that make the clouds that we see at parsec scales, again, not a few hundred parsecs or kiloparsecs, this is too big, a molecular cloud, parsec scale, collapse. So I just add this because it's like a different view. It should be probably much connected, but there is an additional information, which is the inflow material, streamers, we call filaments, we fall in dust and in gas that come in general from outer part of the galaxies or from even the intergalactic medium. That's it. So.
Okay, I don't know if, I mean, there was not a real question, but I don't know if you want me to comment on that or that's, I mean, I'm totally aware that at lower scale, the relations, they don't work. The puzzling is why there are at a higher scale. That's totally agree with you. And I think part of the problem in that you have passed through it, but it's very important, is that this simple interpretation that the Schmidt did and then Kennicutt took later that it's connecting in a molecular cloud that is not existing anymore with the present stars that we see. This was the error. So we keep that all the time in mind, and the molecular clouds that we measure are not the gas that is in the star. The gas that is in the star have already consumed that molecular cloud, and so the connection cannot be in there. So I didn't want to enter on that because it's a complete entire talk, but inflow, outflow, and in particular feedback, it's the line to go. The reason for this is for you are already large scale, because kiloparsec it's a very large if you compare to the size of Orion. This relation have to emerge due to other reasons. It cannot be just by simply adding and zooming of mass. That I think we agree on that. I mean, I don't see a big problem on that. I said before that we were approaching to that thinking of stars like millions of them, tens of thousands, and now individual stars are annoying, but we need to take care of them, you know. So I totally agree. And one of the big problems that we don't communicate, I think I told in my talk in Ensenada, no? Like a couple of months or 3 months or 4 months ago, I don't remember, I cannot remember. It was before Christmas, no? I told that we don't communicate. There are two communities that are working for two different approaches, and now we need to start communicating, because to understand what we see at a larger scale, we need to go to smaller scale. And to understand what is happening at lower scale, you need to go to large scale, because you cannot describe what happened at that scale you are working without understanding why this at the end, this pathway, these individual monsters need to be connected at a larger scale, and the relations should emerge. So, yeah, totally agree. I don't have a problem with that. That means that we need to work more. They pay for us for doing that, so I don't care.
Good point. Okay, the final question, please go ahead.
So it's about the age maps that you showed. So I assume you calculated using the star formation process. But do you use like the H alpha, or do you use like a non-parametric star formation where you divide it into 8 bits to calculate the age?
We make the composition with different single star populations. So you assign a certain amount of light to a certain population, and then you may assign a certain mass to a certain population with a certain age. And from that, you can derive the luminosity weighted age. That is the first moment of the age distribution function. Okay, what you get with this, the composition is an age distribution function, a metal distribution function, and the average weighted by light is this is the luminosity weighted. So indeed, I didn't say, because I took some slides out. It's more interesting to explore all the age distribution, and all the metal distribution gives you more information than just one single value. Average may not tell you all the information, but that's the way we do that. So it's an equation, you know, sum the weighted by light times the age, and that's all.
Yeah, because you can also calculate it using like when you fit the spectra using a model like a non-parametric, where you divide the star formation into different age bins.
Yeah, you can.
And so now my curiosity was if you do one way or the other, and if
what happens? Okay,
compatible or
well, there are some studies where we do that, but we didn't explore the age exactly. But there are some explorations with Sanchez, for example. We explore the star formation rate that you get at the end with these two different approaches, and it matches pretty well when you have enough signal, and it doesn't work when you don't have signal. What is was not very surprising, by the way. The match was recovered pretty well, but the age, in particular the age, we didn't do. But if you get the right star formation rate and you get the right mass, I figure out that apart from the scaling, you will have a very reasonable number comparing both. But I told you that multi-frequency is also important, and that we still have all the complete picture.
Okay, so remember that Sebastián will be here until the next week, the end of the next week. Also, in fact, next Thursday, also give a seminar related with another interesting project, the local volume mapper. Now today we can join the hall if you want to come to have lunch with Sebastián. Okay, thank you, Sebastián, for the talk. It's very great that you stay here at the AIA. I'm quite happy for this seminar because they also put in context the beautiful work that we have done in Khalifa for the rest of the community. So thank you a lot.
Well, thanks to you for inviting me. Pues te vi el otro día pasando por el pasillo,
Sí,
pero,
chill.
pero rápido. Espérate que me desconecte de aquí.
No me puedo quedar hoy para la comida, pero buscamos algún día para tomar un café.
Sí, por favor. Sí.